We are Erin, Alina, and Katy, and we are students at the Beaverworks Summer Institute in the Quantum Software course. Quantum software involves a computing method that increases efficiency and gives us the possibility to solve problems that are not possible classically. Classical computers use bits, which can be 0 or 1, to encode information. Quantum computers, on the other hand, use qubits. Qubits can be 0 or 1 as well, but they could also be both at the same time. This means that they have some degree of zeroness and oneness. For our project, we studied the quantum phase estimation algorithm, or QPE. QPE is an important building block in many more complex algorithms. By itself, QPE can be used to solve for a value, the eigenvalue, in this equation. The left side of the equation consists of a rotation, or a matrix, applied to a register, or an eigenvector. The right side consists of the eigenvalue multiplied by the register. Given a unitary operation affecting the phase of a register, we can compute the eigenvalue. The graph pictured here shows how a matrix, or linear transformation, is applied to the eigenvectors. The eigenvalue is the scalar by which the eigenvector is stretched. We can start by using a register of qubits and an ancilla qubit. The more qubits there are in the register, the more accurate the estimation will be. The register is put into superposition and the ancilla is put into the 1 state. Then, the oracle is applied several times on the ancilla qubit with the register as a control. After an inverse quantum Fourier transform, the register is measured and an integer is calculated from the bit string. The final value is calculated to be the integer answer divided by 2 to the power of the size of the register. Let's run through an example of QPE. We have a register with 3 qubits and 1 ancilla qubit. We'll prepare all the qubits, apply the controlled T-gate, or rotation, and then apply the inverse quantum Fourier transform to the register. After measuring, we find that the expected binary of the register is 001, which translates to 1 in decimal. The final answer is 1 divided by 2 to the power of the register size, 3. 0.125 is the same answer no matter the register size, meaning that the expected binary will change.
First, we implemented the code and unit test in Q#, a language used to simulate qubits for quantum development. We have 7 unit tests that utilize different gates, including the T-gate, the R1 or P-gate, and the S-gate, all which are rotation gates, meaning they don't change the state of the qubit. Additionally, we look at algorithms that use multiple ancilla or target qubits. We wrote tests for those in Q# as well. All those tests ran successfully with the simulator. We then re-implemented the algorithm in Qiskit, a Python library for quantum software so that we could test our QPE implementation on real quantum machines. These machines only use a handful of rotation gates, so they may have to apply several gates to achieve the effect of 1 gate on a simulator. At the bottom of the slide are all the rotation gates that Santiago used for our algorithm, which is more complicated than the original circuit diagram for QPE. The histograms show the frequency of each integer result, and unfortunately the noise in real quantum computers do not allow for precise measurement with our implementation of this algorithm.
At the top of the graph, we have the Aer Simulation, which represents an errorless system. It was able to identify the correct eigenvalue most of the time. We ran the same exact algorithm and test cases on 2 of IBM's quantum computers that we have access to, Manila and Pagoda, and they both performed horrendously. This is likely due to quantum noise present in actual quantum computers. In the real world, it's actually really difficult to get qubits to interact in the way we want them to, especially as the length of the program increases. So we decided to simulate QPE on a more stable machine, IBM's Montreal, and that performed considerably better with almost half of the trials passing. So this brings us to practicality. QPE is not practical for smaller quantum systems, but it is for larger, less error-prone ones. In short, more qubits and a higher quantum volume produces more accurate results. The quantum computers that we have access to only have 5 qubits, which leaves us with 4 bits, or binary digits, of precision. That's not very many bits. So the first challenge we had was with understanding the papers. Because QPE is fairly abstract, there's a ton of math involved. Initially, our group had issues following the intuition and proofs due to our lack of knowledge in linear algebra. We spent the first couple of days stumped on eigenvalues, eigenvectors, and other concepts, but thanks to our instructors and TAs, we were able to sort that out. The second challenge we had was with this concept called endianness. If you are unfamiliar with it, it's basically just how computers read bit strings. To the right is a bit string 1011, which when converted from binary is 11. However, there's another notation that reads bit strings backwards. Instead of 1011, it reads 1101, which converts to 13. Qiskit, the Python library we used, assumes inputs are backwards, or little endian, but the papers we read used a mix of big and little endian, which led us to interpreting incorrect results.
Quantum phase estimation, which solves for the eigenvalue when given a matrix or rotation and an eigenvector, is one of the most important subroutines in quantum algorithms. The classical algorithm for finding the eigenvalue runs with O(n) squared rotations, but the quantum solution has O(n) log 2n rotations, making it much more efficient. The creation of this building block allowed for many more quantum algorithms to be feasible. Thank you.